So today I'm here to talk about net dipole movement. With our first one, our easiest molecule, we have BeCl2. And how to find this is you can find out how many electrons, valence electrons, will make up this molecule. So for Be, you have 2 electrons, and from Cl, you get 7. And since you have 2 of these, you add them up to get 16 electrons. So you draw it out. You do a single bond between the 2 Cl's and the Be, the beryllium. And so from that, you can just add on the rest of your electrons so you can form octets. And you get a total of 16 electrons from here. But the problem is you don't have an octet with Be. But you have to remember Be has less electrons than an octet. That is one of the exceptions to form one of the exception rules in terms of finding an octet. And so Be has a partial positive electronegativity because it is less than Cl. Cl has 3.0 and Be has 2.0 as shown in our electronegativity chart. Through that, you can draw your dipoles, and since it's the same element on each side, your dipoles are exactly the same. So the net dipoles cancel, it is nonpolar, and you can tell that because the molecular geometry is linear, and since they're in different directions, they cancel out. Now, in your next ones, CCl4. So with this molecule, you end up with a tetrahedral shape for the molecular geometry. And so you have 4 Cl's, which are, so you have 4 domains. And since the domains are the same, it is nonpolar. And since your Cl electronegativity is greater than your carbon electronegativity, you have a partial negative charge on each of your Cl's and the partial positive charge on your Cl. So as you can see, the dipoles are facing away from the Cl, but since it is equal in all directions, it is nonpolar. With your SO3, you have it is nonpolar because your net dipole is 0. Once again, it is trigonal planar, however, and due to the electronegativities, you have a greater electronegativity with your oxygens, which are surrounding your sulfur, which is 2.5. Therefore, you can see the partial positive charge with your S and partial negative charge on your O's. And so since they cancel out, your net dipole is 0, so it is nonpolar. With your OF2, it is once again nonpolar because you have O surrounded by 2 F's and they are facing opposite directions. However, unlike the first one, it's not linear, it is bent because you have non-bonding electrons, but everything else is basically the same. You have your partial positive charge in the center and your partial negative charges on each side because the outside elements, the fluorine, is a greater electronegativity as opposed to the O because F is 4.0 and O is 3.5. For your final one, for ozone, O3, it's different. It is a resonance hybrid. That's because you would think that one side has a double bond and the other side has a single bond. However, we share the bonds because you can have one double bond on one side and one double bond on the other side. It can be written any way from 2 bonds right here and 1 bond right here, or 2 bonds right here and 1 bond right here. So in order to display that, we do a dotted line, which shows that we can share the bond, and so it's approximately 1.5 bonds on each side. Therefore, it is bent, and in the end, it is polar. Some mistakes you could make while doing this, while just finding your net dipole movement, could easily be you don't know how to figure out molecular geometry, and through that you would have to draw out the correct, well, you'd have to have the correct domain geometry, and for you to properly do that, you would need to have proper Lewis structures drawn. Also, you could not know about the octet exception, an example for number 1, or just not know about resonance hybrids for number 5, and just overall be quite confused with that, or just not know how double bonds and single bonds work, and just calculating out the total amount of valence electrons you would need to have. And this concludes my presentation on net dipole movement with 5 example compounds.